All right, so we are finishing up 5.2, kind of. There's still one more topic in 5.2 we'll go over on Wednesday. We're looking at operations with radicals and simplifying radicals. We're first going to look at this division, similar to what we did with imaginary numbers. We had to multiply by the complex conjugate to divide imaginary numbers. We have to multiply by the conjugate. It's not complex because it's not imaginary when we're dividing radicals like this. When the radical is a binomial, a radical and a number, then I can't just multiply by the square root of 7 to get rid of it. I have to multiply by the opposite of the radical, so negative 7 minus 2, or negative square root 7 minus 2. Okay, so we multiply by the conjugate, and it's the negative, the opposite sign on the radical. And whatever I do in the bottom, I have to do in the top. I can't change both signs because if I do that, then the radicals don't eliminate. Okay, so when I multiply 1 times negative 7 minus this negative square root 7 minus 2, I get negative 7 square root 7 minus 2 in the numerator. But in the denominator, I have to multiply these two binomials. I have to treat these as if it was like x minus 2 times x minus 2. And I have to multiply it out. Remember, we used to do vertical multiplication. So we're going to multiply negative square root 7 minus 2 times the square root of 7 minus 2. We're going to do the multiplication like that. Or you can use FOIL if you like that method better. So remember here I do negative 2 times negative 2 is what? 4. Positive 4. Then I have negative 2 times negative square root 7, which is positive 2 square root 7. And then square root 7 times negative 2, negative 2 square root 7. And then square root 7 times negative square root 7 equals what? Negative 7. Right? Because square root 7 times square root 7 is the square root of 49, which equals 7. Okay, so the radical disappears. And then when I combine my like terms, my square root 7s are gone, right? 2 square root 7 minus 2 square root 7 is 0. And then I have negative 7 plus 4, which equals negative 3. So my answer is this over here. Yes, you could use FOIL if you wanted instead. Okay, we'll do another one. 1 over 3 minus the square root of 5. So what is my conjugate? 3 plus the square root of 5. I only change the sign on the radical, okay? And if there's 2 radicals, I only change the sign on one of them. So the top is just 1 times 3 plus square root 5, so that's just 3 plus the square root of 5. And then we need to multiply 3 minus square root of 5 times 3 plus the square root of 5.
Will the top always be the same?
No, if the top is 2, then you distribute the 2.
Okay.
Right? The 3 and the square root of 5. So it would be, like if this was a 2, then we would get 6 plus 2 square root 5. Okay. So let's see. What is the square root of 5 times negative square root of 5? Negative 5. And the square root of 5 times 3? 3 square root 5. And 3 times the negative square root of 5? Negative 3 square root 5. And 3 times 3 is 9. So we get 9 minus 5 because the square root 5's cancel. And we get 4. So 3 plus square root of 5 over 4 is my final answer. Okay. B. Adding and subtracting. So to add or subtract radicals, they must have the same index and radicand. Here's some vocabulary for you. In the radical, the number underneath is called the radicand, and the number of the root is the index. They have to be like terms. Just like I had to have the same variable and exponent to add up polynomial terms, we have to have the same index and radicand. And if we're looking at it in fractional exponent form, it has to have the same base and the same exponent. Okay. So, for example, 6 square root 7 and 6 square root 7. 12 to the 1/5 power and 12 to the 1/5 power. You can add those up. There'd be 2. Example 1. Six square root 7 plus 9 6 square root 7. I'm adding up how many I have. How many are there? 10, right? If that was x plus 9x, we would say it's 10x, right? If this was just x plus 9x, there would be 10 of them. So there's a 1 in front, right? So I have 1 square root 6 root of 7, and I'm adding 9 more, so I end up with 10 6th root of 7. So think x plus 9x equals 10x. That's kind of what we're doing. Example 2. What if it's in exponential form? I have the same base and exponent, so I can combine them. It's okay. I have 5 and 6. How many are there? 11. What do I have? 7 to the 1/3 powers. So we're really just combining the coefficients in front when we're adding and subtracting. But they have to be the same. Same base and power, same root and the number underneath. What if it's not the same? Well, what if we can simplify it? We have the 4th root of 48 minus the 4th root of 3. Clearly, I don't have the same radicand, but can I simplify 4th root of 48? How? 6 times 8. Right? 3 times 2 times 2 times 2 times 2. So I have my 4 2's. So I get 2 4th root of 3 minus the 4th root of 3. Now I can subtract, right? Remembering that there's a 1 in front. What do I get? 1 4th root of 3. Oh, sorry. Questions? All right, so part C, simplifying variable expressions. We simplified radicals, but now we're going to add some variables in there. We have the cube root of 27d to the 12th. Now, remember that the cube root can also be written as a 1/3 power, right? So I can do the cube root of 27, right? Which is what? 3. Then I have the cube root of d to the 12th. Okay. So which could be d to the 12 over 3, right? The exponent becomes the numerator, the root became the denominator, and I end up dividing, right? So I can divide my power by my exponent or my root to simplify, because it's the same as multiplying by 1/3, which is dividing by 3. So I get d to what power? To the 4th, 12 divided by 3. Okay, so we can divide the exponent by the index, or the root number. Okay. So how about that? The 5th root of 243x to the 20th. 3. The 5th root of 243 is 3, right? And I can divide my power 20 by my root 5, and what do I get? X to the 4th. We run into a little situation when we do something like this. Do you remember doing this on the homework? Oh, that wasn't it. 4th root of -2 to the 12th. Do you remember plugging that into the calculator? Yeah? Anybody remember what we got out? Not if we put it in right, we didn't get an error. If you put it in with 2, you needed to have put this in with a second set of parentheses, and you got 8. Let me show you. To evaluate this, we needed to do the 4th root of parentheses, -2, close the parentheses, to the 12th. Close the parentheses. If we don't put that second set of parentheses in there, this set, it stops the root at the -2, and that's why you got an error, because it tried to take the 4th root of -2. But when you take -2 and raise it to the 12th power, it becomes positive, right? And then you can take the 4th root of it, and we get, well, I used minus instead of negative. Then we get 8. Okay? Again, we can't use the minus sign in place of the negative sign.
Wait, where's your 4th parentheses? Because I only saw 3. Did the other parentheses go after 12?
No, there's only 2. After the 12, there's 1.
Okay.
Yeah, and you don't actually have to put the 1 after the 12 in. It'll still calculate it correctly. But, so we know this should be positive 8, right? Because when I take a negative to the 12th power, it becomes positive. And then I take the 4th root of that, it's positive. But if I use my shortcut and divide my exponents, I get -2 to what power? To the 3rd, which equals -8.
Let me write this down.
Right? Is it -2 to the 3rd power? -2 times -2, which is +4, times -2, which is -8.
What's the right answer? Okay, so why is the calculator?
Because 8 is the correct answer. We are doing a shortcut when we divide. And so we need to do something to make sure we recognize that because we had an even exponent under an even radical, the answer is always going to be positive. What do we have? What kind of function do we have that turns all of our negatives positive? That's not a square. No. Absolute value, yes. Absolute value takes that and says, okay, I recognize that this answer should come out positive because I'm raising a negative to an even power, so that's going to be positive. But when I use the shortcut, it comes out negative, so we have to put the absolute value around it. So this is a rule that happens when we have, okay, an even index or even root with an even power, and the answer has an odd power. This problem arises when we have an even root of an even power and the answer comes out odd. And we need to put the absolute value around it. If the answer came out even, it's still going to be positive because a negative to an even power is positive, right? So we only need it when it comes out negative. And we don't need it on odd roots because odd roots can be negative. And it doesn't work if we have a negative in here, an even, and an odd. If we have an odd under the radical, if that's negative, it's no solution. So that doesn't work. So we only need it. So we need absolute value. When the even index, the even root of an even power has an odd exponent. For the answer. So EEO, even, odd. Yeah, we're going to do some. So we're going to apply it. So we have the 4th root of x to the 4th over y to the 16th. So if I divide my exponents, what do I get on x? My exponent and my root. I get x to the 1 power, right? And y to the 4th. Now, I have even, right? The 4 is even. The 1 is odd. So I need absolute value on the x. And I don't really need to write x to the 1 power, but I'm there so you can see the odd. Do I need it on the y? No, because it came out even. The exponent is even on the y. It'll always be positive anyways. So it's redundant to put it around there. Okay. You don't know what x is. So right now, x could be anything. So for any value of x, in order for them to be equivalent, we have to say the absolute value of x. Because if it were negative, and I were to simplify it by dividing the exponents, then I would get negative. There will be some problems where it says assume all variables are positive, and on those we don't have to worry about the absolute values. Okay, but that's what I was going to erase. I was going to erase the 1.
Make it 4.
Like number 4? Like example number 4?
Oh. Wait, so that's the answer to number 3?
Yeah.
With the x and the absolute.
Yeah, the absolute value of x divided by y to the 4th. Let's do the 4th root of 16y to the 20th over x to the 24th. Okay, give this one a try.
The base is the same, right? 16, 16.
No, you do the 4 through to 16.
Hold up.
So the 4th root of 16 is what? 2. 20 divided by 4 is y to the 5th. And 24 divided by 4 is 6. So x to the 6th. Now, did I have a situation where my went even, even, odd? The denominator is not. It went even, 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 right? But my numerator went even, even, odd. So that needs the absolute value around the y to the 5th. I don't need it around the 2. It doesn't really hurt if it's around the 2. 2 is positive. It's just positive 2. But it's only the variable that really needs the absolute value.
So it's just reducing it. If it ends out odd, it just means
Absolute value, yeah. If it ends out odd from an odd root.
okay. Would you mark us off if we put it around the whole thing?
Yes.
I would change the answer if we put it around the whole thing. Like if you included the 2.
We want to know that you understand where the absolute value is necessary, not just throwing absolute value signs around everything. To be careful, right? We want you to understand where it belongs. Yes. Okay. And then example 5. I'm using a lot of 4th roots because square roots are, well, let's just use the square root. Square root of 3y to the 14th. What's the index on the square root? It's 2, right? So that becomes 3y to the 7th. It's a square root, so that's always a 2 if there isn't a number there. And 3 to the 7th. I need absolute value, don't I?
Oh, okay. Hold up. I'm like, why are you putting it around the whole thing if it has the parentheses?
Because it has the parentheses, yeah. Even, even, odd. Came out odd. I need the parentheses.